and welcome to the proof of the Collatz Conjecture, the subtraction machine. My name is James P. Moore. The Collatz Conjecture. It has been said it's an extraordinarily difficult problem, completely out of the reach of present-day mathematics. Lothar Collatz was a German mathematician born in Arnsberg, Westphalia. The 3x plus 1 problem is also known as the Collatz Conjecture, named after him, and has been unsolved since 1937. Consider these Collatz numbers: 7, 22, 11, 34, 17. Virtually random, it would seem. To start, we need clarity. The Collatz conjecture is one of the most famous unsolved problems of mathematics. The conjecture asks whether repeating two simple arithmetic operations will eventually transform every positive integer into 1. It concerns sequences of integers in which each term is obtained from the previous term as follows. If the previous term is an even integer, the next term is 1/2 of the previous term. If the previous term is odd, the next term is 3 times the previous plus 1. The conjecture is that these sequences always reach 1, no matter which positive integer is chosen to start the sequence. Indeed, it has been said that the Collatz conjecture is the most dangerous problem in mathematics, one that young mathematicians are warned not to waste their time on. To begin, we pick a number. The Collatz conjecture is based on a simple premise. Pick an integer x between 1 and infinity and do one of these two things depending on whether it is an odd or an even number. If it's even, divide the number by 2. If it's odd, multiply the number by 3 and then add 1. For example, if we choose x equals 7 to be an odd number, and because it's odd, we multiply by 3, and then we add 1, giving us 22. Then we do it again. 22 is even, so we divide it by 2. 22 divided by 2 is 11. And then again. 11 is odd, so 3 times 11 plus 1 is 34. 34 is even. 34 divided by 2 is 17. 17 is odd. 3 times 17 plus 1 is 52. And it keeps going. 52 to 26, 13 to 40, 20, 10, 5, then 16, 8, 4, 2, and eventually leaving us with 1. When we get to 1, something happens. We run into this loop. See, 1 is odd. We multiply by 3, we add 1, we get to 4. 4 is even, we divide it by 2, we get to 2. 2 is even, we divide that by 2, we get 1, and it repeats. The conjecture is that any integer chosen to begin with eventually ends up at 1 every time. And it has for every number ever tested. But they don't know the reasons why. It hasn't been proven mathematically. Now, if you play with the numbers long enough, you'll find one of these. They call it a Collatz tree. Do it for a lot of numbers, like I have here. And you start to see things a little different, and it starts to clarify. Here is a much more complicated way of looking at them. From a purely artistic standpoint, Collatz trees can be beautiful. But it really is an enigma. See, for the most part, the journey takes a reasonable number of steps, and depending on the size of the number, patience is all that is required. Consider starting at the number 26 here on the screen, for instance. It takes 10 steps to get to the end, 4, 2, 1. However, Every now and again, something strange happens. Instead of using 26, if we choose the next number 27, all of this happens. We still get to that 4, 2, 1, but for no apparent reason, way more steps. The sequence takes 111 steps, 41 in odd, 70 in even. To climb as high as 9,232 before descending to 1. Needless to say, it is very unpredictable. Now this is what we're taught. 3x plus 1, or x divided by 2. Let's start at 7. It's an odd number, as you can see in the top left. 3x plus 1 gives us 22, correct? That produces an even number, as you see on the right side. Divide that by 2 to get 11. It's half the size. That 11 goes back to the left side, 34. 34 divided by 2 is 17. 17 times 3 plus 1 is 52. 52 divided by 2, 26, and on it goes. Here we notice a couple of important features that hold as facts for every integer x. Every odd number results in an even number after 3x plus 1, every time. And an even number can produce either another even number or an odd number after you divide it by 2. This is different unless the even number is a factor of 2 to the x, and then every division will produce an even number 1/2 the value of the previous until we get to the magic 421 in a hurry. But that's not actually what happens. This is a number line, an integer number line. If we start at 7 from our example, 7 is just one number. After we do our 3x plus 1, this happens. We get 22, a singular number on an infinite number line. We divide that by 2, another singular number that we will apply a mathematical formula to. That's all. We keep going. 11 becomes 34. 34 becomes 17. 17 becomes 52. Again, a singular number and a single mathematical function. 26, 13, 40, 20, 10, 5, 16, 8, 4, 2, and finally 1. It is not until you step away from the visuals of a Collatz tree and focus just on the numbers that it becomes clearer. Using the subtraction machine. See, when you think about it as a machine, it changes everything. And just to have some fun, imagine this machine. Walk on up, he says to the crowd. Walk on up, put your dollar coins in the machine. 2 things can happen. If you put an odd number of coins in the machine, it will work its magic, and 3 times the coins you put in plus 1 will show up in the window. Do we get to keep the coins, someone asks. No, not yet. See, if the dollar coins in the window are an even number, the machine will divide the coins in half, subtract half of them, and that amount will appear in the same window. If that amount is an odd number of dollars, the machine will do that 3 times plus 1 again. We keep going to see what happens. Now, who's feeling lucky today? Well, a young man walks up, puts in 7 $1 coins, pulls the lever, and just like that, $22 shows up in the window to everyone's delight. Well done. 22 is an even number. Let's pull the lever again. 22 became 11, and everyone groaned. Now, that's okay. That's an odd number. Pull the lever again and see. $34 showed up to everyone's amazement. And on it went. 34, 17, 52 to everyone's delight. You got 'em now, somebody yelled. Then 26 to 13 to 40 to 20 to 10 to 5 to 16 to 8, then 4, then 2, and finally 1. Well, I'm afraid to say that's as low as the machine goes, my friend. But the dollar is yours. Let's give 'em a hand, folks, for trying. Who's next? It's the machine. And it's the 3x plus 1 that the machine changes, actually clarifies. It isn't 3x plus 1, it's actually 2x plus 1. See, we start with the $7, and the 3x plus 1 gives us 22. But note that the machine only adds $15 to get there, which is 2 times 7 plus 1. Now the $22 after that, it's even, so it gets divided by 2, essentially subtracting 1/2. So for an odd number, this is what actually happens. There is an addition in the machine and then a subtraction. In this case, an addition of $15 and a subtraction of 11, leaving a net gain of $4 from the odd value that we started with. $7 plus $4 equals 11. This happens for every single odd number. In this case, every odd dollar amount. Continuing, $11 becomes $34. But we have only added $23, which is 2 times $11 plus 1. Then $34, subtract 1/2, which is 17, because $34 is even. The net gain is the amount added, which was 23, minus what we subtracted, which is 17, leaving us a net gain of 6. 11 plus 6 equals 17. Let's continue. We left with $17. This becomes $52 and then $26 after we subtract 1/2. This is where it's very important. See, as soon as we find just an even number alone after the above, like 26, we divide it by 2. We subtract 1/2 the number's value. There's nothing to add. It is just subtraction, in this case, $13. It then becomes a running total. For clarity, consider this example starting at 7. $7 is an odd number. It becomes 22. What we're actually adding is 2x plus 1, which is $15. From the 3x plus 1, we divide that by 2. We've added 15. We've accumulated 15. We subtract 11. When we take that into consideration, the addition minus the subtraction equals 4. 7 plus 4 equals 11. Follow along here. Start with 11. It's an odd number. That becomes 34. We've only actually added 23. We subtract 17. 23 minus 17 is 6. 11 plus 6 equals 17. That's our next number. And on it goes. If you just follow the math here, every odd number, we add a bit, and then we subtract half of it. For every just even number, we subtract half of it. Eventually, we reach 1. If you look at the two columns, accumulated added and accumulated subtracted, at the bottom there, you'll see that accumulated added was 111 from the beginning of 7, so for 118. The accumulated subtracted was 117. 118 minus 117 is 1. From the starting value of 7 plus all that was added minus all that was subtracted, we get to 1. Happens every time. This is what the subtraction machine teaches. Now let's look at an all-even example, starting with the value 256. It's an even number. We have to divide it by 2, which is basically subtracting half of it. Same columns. On the far right, you see there's nothing added. We're subtracting half. 128, and we're left with half of it, 128. That 128 becomes the starting point on the far left. Divide that by 2, subtract a half. And you see we're not adding anything. That becomes 64. 64 becomes 32, and on it goes until we reach 1. Now, there's nothing that we added. The accumulated subtraction is 255. We started with 256. 256 minus the subtractions equals 1 every time. Now, just for fun, if you've got some time, try it on any positive integer. It works every time. It has no choice. The machine has taught us, has given us the solution to the Collatz mystery. For any positive starting integer value x, if x is odd, multiply it by 3x plus 1. This increases x by 2x plus 1, the amount added. This step always creates an even number. For any even number x, divide the even number by 2. This is the equivalent of subtracting 1/2 of it. The result will always be the same. Starting value plus amount added minus the amount subtracted gives us the result, whether it's odd or even, for every integer. Now, for all subsequent odd and even numbers, the process is repeated. The machine is always the same. Once the value of 1 is achieved, it always will because of the above, we find that the total amount added and subtracted during the calculations, when applied to the starting integer value x, will always result in a final value of 1. So, for any positive starting integer value x, that starting integer value x plus the total added minus the total subtracted equals 1 every time. Now what's happened here is, by considering the Collatz operations as addition and subtraction instead of multiplication and division in a machine setting, both the processes and the reason for the inevitable result of 1 become clear. Some observations. It's clear that 2x plus 1 is the additive component to the odd integer process, and importantly that 3x plus 1 divided by 2 is the subtractive component to the odd integer process. These two equations combine as 2x plus 1 minus 3x plus 1 divided by 2, and you get 0.5x plus 0.5 for all odd numbers. However, for any even number, the result is always subtractive, minus 0.5x, or basically halving it. Any even number x, when divided by 2, can produce either an odd number or an even number. For example, 20 divided by 2 is 10, whereas 34 divided by 2 is 17. There is a short answer as to why this is important, why there is a clear tendency for numbers to descend in value eventually. For every even number, 1/2 of the value is subtracted for each. The result is either an odd or an even number. If it's an even number, 1/2 of the value is subtracted for each. If it's an odd number, 1/2 of the value is subtracted for each after 3x plus 1. So the short answer is 1/2 of the value is subtracted for each. Consider the top row of these odd numbers to begin. 1, 3, 5, all the way up to 27. After multiplying the top row by 3x plus 1, we get all even numbers, of course. Now, as previously shown, 50% of the time dividing by 2 brings you back to an odd number. But 1/4 of the time, you can divide by 4 before you get to the next odd number. So, for a quarter of numbers, the next one in the sequence will be 3/4 of its initial value. And 1/8 of the time you can divide by 8 before getting to the next odd number. And 1/16 of the time you can divide by 16 and so on. If you take what's called the geometric mean, you find on average to get from one odd number to the next one, you multiply by 3/4, which is less than 1. The 3/4 shows that statistically, 3x plus 1 sequences mathematically decrease rather than grow over time. I'd like to thank Veritasium for that quote, but that is the long answer. Remember this from a few slides back, x equals 27. See, every now and then, this happens. Perhaps we choose the next number to be 27. Now, we still get to 421, but for no apparent reason it climbs as high as 9,232 before descending to 1. The sequence takes way more steps, 111, 41 steps through odd numbers, and 70 steps through even numbers, each step cutting the value in half. This is the reason for the previous 2 pages. Over time, subtractions by half the number's value dominate. This here, x equals 27, is a unique case of odd, then even, and it slowly grows until 9,232. But then the laws of mathematics take over, and we get this even 9,232 followed by 3 more evens in a row, followed by 8 evens out of the next 10. Taking us down from 9,232 to 61 in a hurry. Remember that short answer. 1/2 of the value subtracted for each. Like anyone who has enjoyed the Collatz Conjecture exploration, I have very large pads filled with paths of thought, much like a Collatz tree in so many ways. One day the engineer part of me became curious, and to clarify Collatz, I imagined a machine that would duplicate the workings of the mathematics precisely for any integer number of identical physical items you placed into it initially. Once the machine started, it would perform the odd-even tasks physically for each step. And there it was. A machine confirmed and clarified the mathematics of the Collatz conjecture in a clear and undeniable manner by introducing physical addition and subtraction. I'd like to thank you for watching or listening. The mathematical declarations are as follows. The symbol for all integers x, large Z, comes from the German word Zahlen. The Collatz conjecture only applies to all positive integers 1 through to infinity, mathematically inclusive as defined. There are no exceptions. The 4 basic arithmetic operations in math, addition, subtraction, multiplication, and division, for all integers are timeless, immutable, and infallible. Infinity is that which is boundless, endless. There are no exceptions for all positive integers. The subtraction machine equations, 3x plus 1, x divided by 2, and 2x plus 1 that are based on the above are timeless, immutable, and infallible for all positive integers from 1 to infinity, mathematically inclusive. These equations and their applications completely define the Collatz conjecture for all integers and prove that for any positive integer x, these equations will always result in a final value of 1. This proof is in honor of Dr. Lothar Collatz. Sir, you created a perfect mathematical machine.